Hey everyone. In this video, we're going to be talking about torque and the rotational analog of Newton's second law. Um, we are going to proceed in a very similar fashion as we did in the last video, where we just kind of make analogies between rotational dynamics and linear dynamics. And so I think the first thing I want to do is say something conceptual about what torque is. So what I would say is this. I would say inasmuch as a force can be thought of as a quantity that tends to make an object accelerate linearly, torque can be thought of as a quantity that tends to make an object accelerate angularly. Is that really a word? Okay, anyway. So remember what we mean when we say something is accelerating angularly. That just means that its angular velocity is changing, right? And this is perfectly analogous to the linear case, stuff that we were discussing in week 1. Okay, so I want you to just keep that in mind as we go through this. Okay, so the mathematical definition, though, of torque is, and this is a cross product, okay, times F. And these, I'll fix that in a second, but those should be vectors, right? And I will make them vectors. But what this means, right, is as with any cross product, we can solve for the magnitude by applying something like this, right? Just the magnitude of the r vector times the magnitude of the f vector, and then tack on a sine of theta, right, where theta is the angle between them. So let's see here. Ooh, I just had something I wanted to say, but I totally forgot it. And the unfortunate thing is that I pretty much deleted all my notes right before starting recording here. And so this is going to be very improvisational. Hopefully it's not awful. I guess we will see. Okay. So what I want to say that it actually occurred to me is that, so we know what a force vector is at this point, right? Hopefully, but this r vector thing, it might be a little bit hazy. So what I'm going to say is where r is the vector that takes us from the point about which we'd like to compute the torque to the point at which the force is being applied. And we will see an example of this very soon, in case it's not clear what exactly I'm saying by this. But looking ahead, the idea is that there, for a given setup, right, there could be many different ways to specify the torque, because we could always just choose a different point in 2D or an axis in 3D about which we would like to calculate the torque associated with a given force, right? And so that's an important idea about this, and it will be very important when we start working with static equilibrium problems, which we will do in the next video. Okay, so let's see here. So there's that, and what I want to say is, I have a lot of things to say, but let me just say, first of all, the dimensions, right? Dimensions of torque are, and this might be a little weird, right? So we're going to have a length for r, and then we're going to have a mass times a length over a time squared, right? And so we find that this is a mass times a length squared over a time squared. Okay. Now, why did I say this is weird? Well, let's think about the units of this, right? The associated units will be, well, they're going to be Newton meters, right? Because we have a force times a length. And this is not the same Newton meters that we associate with work, right? And what I mean by that is that the units are the same, right? The Newton is always a Newton, a meter is always a meter, but we would never say that the units of torque are joules, right? And so here you'll always write Newton meters. Do not convert this to joules because that is just not correct. And the best way I can explain this is it's a convention, right? Whereas work, which has dimensions of energy, can be thought of a force being applied over a distance, whereas torque is, when it comes down to it, a distance times a force, right? And so they're physically very different, even though they have the same units. It's kind of really weird, right? But hopefully we can just all accept that and move on with our lives here. So I wanted to say just a few more things with this definition in mind. I'm going to say that note that forces cause torques, right? And an equivalent way to express the magnitude of the torque is, and we could write it like this, we could write magnitude of the torque is just the perpendicular component of r times F, or equivalently r times the perpendicular component of F. And we'll see what this actually ends up looking like, practically speaking, when we work some problems here. And I think that's it for the definition of torque and the different ways we can express it and what it means. So let's look at an example here. So this is just a very abstract example, right? It's just some force being applied at some position. But let's see what the torque is here. So I'm going to bring the whiteboard over, and we can make a sketch of this. So maybe let me put that here. So we want to draw our usual x, y axes, right? And if, let's see here, let's draw the position vector first. And so that's going to look, maybe we go 3 units to the right, 2 units up. That could look maybe something like this, right? Now let's try to sketch the force vector. And that is going to go -10 to the left, or not -10 to the left, 10 to the left, right? -10 to the left would be to the right. 10 to the left and 5 up, so that should look maybe something like this. Okay, so what we have is we just have a force and a position vector, right? And the main reason that I wanted to sketch this is just to convince you, even though you probably didn't need to be convinced of this, that these vectors, right, the force vector and the position vector, they lie in the xy plane, which means that our torque is going to point either in the positive z or negative z direction, right? And if I redraw my force, let's say I just move it down here so we have maybe a clearer picture of the angle between these two vectors, from the right-hand rule, I can already see that the resultant here, well, I shouldn't say resultant, but the cross product, right, the z component of the torque will be positive. So the torque vector will point like out of the screen toward your face in this case. So let's calculate that, and I'm going to do this via the component definition of the cross product, right? So from the definition of the cross product, we can probably see that the torque vector will only have a z component. So we calculate it, right? We just write something like this. We can say that tau sub z, and thinking back to our very first lecture, right, what we would get trying to calculate this via the components is something like this. We would get the x component of r times the y component of f minus the y component of r times the x component of f, okay? And so we just fill this in. Let's see, how do I want to do this? I'm going to just put the numbers in the square brackets here and the units outside, which is a perfectly okay thing to do. So the x component of r is 3 meters, and the y component of the force is 5 newtons. Okay, so we get 15, and then minus, now the y component of r is 2 meters, and the x component of the force is negative 10 meters, or newtons, sorry. And so what we find here is this should work out to be 15 plus 20, so 35 Newton meters, okay? So if we want to express the torque, right, expressing this as a vector, we could write something like this. We could just write that the torque vector is given by the ordered triple where the x component is 0, the y component is 0, and the z component is 35 Newton meters. And this indeed points in the positive z direction, right, which is what we expected based on our intuition for the cross product, right? Okay. So that's it for this example. Just like I said, a very abstract kind of computational example, but hopefully you see how this is computed kind of in a very general sense now. So let's look at the second law again, Newton's second law, right? I mean, who else's? And what I want to say is recall Newton's second law. And I'm going to do this in one-dimensional, or the one-dimensional case as I think I've been doing. But, of course, in its full generality, Newton's second law is a three-dimensional thing, but there's no harm in just focusing on the x direction, I think. So, from the last lecture, we suspect that the angular acceleration, right, which was alpha, will take the place of the linear acceleration, which is just a sub x. And we already stated, right, that forces cause torques. So we also suspect that the net torque, well, I spelled it right. Why are you not substituting sigma? Okay. The net torque, and I'm going to say in the z direction just because if we usually tend to think about our force vectors and our position vectors as being in the xy plane, then the torque will always have a z component, right? I mean, it might be 0, but if it's non-zero, it will point in the positive or negative z directions, right? And so I'm going to say that we also suspect that the sum of the torques, and in as much as this term here means the sum of the forces in the x direction, right? This means the sum of the torques in the z direction. So we also suspect that this will replace sigma f sub x. And so that really just leaves the mass, right? And so let me just say, but what about the mass? And the way that we replace the mass is with this idea of the moment of inertia. And so we need something to replace the mass in the linear case that accounts for how the mass is distributed in space, right? Because that wasn't necessarily something we were super concerned with when we were working with Newton's laws, right? But now it's going to be important, and I don't know that I can justify this. I'm just going to say, trust me, there's a common sort of demonstration where, a physics professor will get into a chair that can spin, right? And we'll have like a student spin the professor around, and the professor will, like hold their arms out or pull them in, and you can sort of see how the angular speed changes when the distribution of mass changes, right? And that is typically done when talking about angular momentum, and I will probably show you something like that when we get to that topic, but for the time being, I'm just going to ask that you trust me that we need something that accounts for how the mass is distributed when we're talking about torques and rotation in general, okay? And so I'm just going to jump right into defining the moment of inertia for a collection of point masses. So let me say this. Let me say for a collection of n point masses, the moment of inertia is defined to be, and we're going to do this as a sum, right? We usually call the moment of inertia I, and we're going to take a sum like this from the first mass to the nth mass, where what we're summing is the mass of the point mass and its perpendicular distance from the axis of rotation squared, right? So let me just put that in the document here, and I'm going to say where r sub I is the ith mass's perpendicular distance from the axis of rotation. And we'll check the dimensions. The moment of inertia has dimensions so we see that it should just be a mass times a length squared, and thus corresponding SI units of kilogram meter squared, right? Okay. So there's that. And I think we'll just look at an example. Well, before we jump into the example, what I'll say is that this is another thing like the center of mass that could be calculated with integrals, right? But the integrals that you usually have to compute to determine a moment of inertia are even more awful than the integrals for center of mass. So I'm going to probably not even touch this. But maybe if you're in like Calc 3 or something, you'll see an example of how this could be done. But we're not really going to worry about that so much. Okay, cool. So then let's look at an example here. Okay, so the example is a point mass of m equals 2 kilograms is fixed to one end of a negligibly massive rod with length L equals 0.8 meters, and another point mass of big M equals 5 kilograms is fixed to the other end. What is the moment of inertia of this object? Okay, now this is kind of a loaded question, and let me just say Well, it depends. We have to first define an axis of rotation. And so I'm going to sketch this, and then I'll draw in my axis of rotation. So let me get the whiteboard back up. And what this might look like is, say we have the smaller mass here on the left. This is the rod that connects them, and the larger mass is over here. So this length is L, and we have little m here and big M here. Now, a very natural choice to make here would be to just calculate, or rather to set the axis of rotation at the midpoint, right, of the rod, and this is probably what most people would do. And so let's do that, right? Let's say this is our axis of rotation. Now, if we want to imagine how this thing would spin with this being our axis of rotation, it's going to, it's actually hard to describe, but it's going to spin around such that both the masses stay at a constant height, right? So after this thing has spun for like, I don't know, like 180 degrees, right? The big mass would be on the left and the small mass would be on the right. So try to visualize this. If you need to, you can maybe like take a pencil and twirl it around horizontally and get an idea of what this kind of looks like. And the reason it's going to rotate this way is because of how we defined our axis of rotation. And so let's calculate this, right? Though let's see what we end up getting. And remember that for point masses, and I didn't say in the problem statement, but we can imagine these are spheres, and spheres are very symmetric, right? So we can always pretty much take a sphere and think of it as a point mass. And so our definition was this, right? I equals 1 to n of m sub I r sub I squared. And so here we would just have something like the moment of inertia is the first mass, and it is L over 2 away from our chosen axis of rotation, right? And we square this, plus the other mass, the big M, and this is also L over 2. L over 2 away from our chosen axis of rotation. So this is what we find, and we can simplify this. We can write something like 1/4 m L squared plus 1/4 big M L squared, right? And this just ends up looking like 1/4 big M plus little m L squared. Okay, and so I'm going to say, if we define our axis of rotation to pass through the midpoint of the rod, then we find, I'm just going to put the result from the tablet right here. Like this, right? And this isn't so bad. But now maybe let's look at another way we could define our axis of rotation. I'm not going to do obviously every possible way because that would take forever, literally. But what I want to just kind of talk about very briefly, and I probably won't even put this in the document, but like let's now imagine that we want to take our axis of rotation to be through the smaller mass, right? And so in this case, our moment of inertia would simply be, I'll call it all I prime, would just be big M times L squared, right? Because this one is zero distance, right? I could write r sub I for this one is zero distance away from the axis of rotation. And so the point of all this is that the moment of inertia you calculate very much depends on your choice of an axis of rotation, right? And so before you start trying to calculate, a moment of inertia in a given problem, make sure that you've specified what your axis of rotation is. And then just crank it out, right? Okay, cool. So we're going to talk about the parallel axis theorem. And this is a way, let me just put this in words here in the document. Say, the parallel axis theorem gives us a way of finding the moment of inertia of an object about an axis of rotation that does not pass through the object's center of mass. And I should say, providing that the axis of rotation we want is parallel to the axis of rotation passing through the object's center of mass. Let me just check this and make sure that I like this way of phrasing it. About an axis of rotation that does not pass through the object's center of mass. Okay, and this all hinges upon us knowing what the moment of inertia of the object is when our axis of rotation passes through the object's center of mass, right? And what I want to do is just find a quick table of moments of inertia for common objects that everybody can use freely. So give me a second here. The moment of inertia table. Okay, I think I like this one. Let's see if this will work. Yeah, wow, nice. Okay. Let me just adjust the size here since it's kind of large. So this is a table of some commonly encountered moments of inertia. And we'll come back to the parallel axis theorem in a second. But this is a table of some of the most common moments of inertia that we'll need, right? And we have some pretty, nicely symmetric objects here. We have a cylinder or disc, right? We have a hoop or like a ring, a solid sphere, a spherical shell. So this could be thought of as, well, the solid sphere could be thought of as maybe like a bowling ball, right? Where it has a uniform density. And a spherical shell could be thought of maybe like a beach ball, right? Where the inside is hollow. And obviously they have different moments of inertia, as you can see. And then the last one would be for a rod about its center and a rod about one of its endpoints. And these dotted lines, or just straight lines here, these indicate the axes of rotation, right? But let's come back to the parallel axis theorem, because this is something you can find in your textbook. Probably any intro physics textbook will have a table like this. So what I wanted to say, though, is that mathematically, the parallel axis theorem is expressed, and I'm going to write this. I'm going to write I prime, and we'll unpack this in a second, equals I center of mass plus, let's say, md squared. Okay, so we need to probably talk about almost every term here. So let's start with I prime. So I prime is the moment of inertia about an axis parallel to the axis passing through the object's center of mass, I sub cm is the moment of inertia of the object about the axis. I should say an axis because there can still be more than one. Let me say about an axis passing through the object's center of mass. Let me just check the verbiage here, make sure I like this. Oh, I misspelled mass. I don't like that. Okay, I think this looks good so far. And then m is the mass of the object, and d is the perpendicular distance from I sub, well, from the axis corresponding to I sub cm to the axis corresponding to I prime. And we will work an example, a very sort of canonical example of this, basically right now. And hopefully it becomes a little bit clearer as we do this example. So I think that's all there is to say about the parallel axis theorem. And as I said, got a table of moments of inertia, and that's nice because we are going to need it. And what we want to do for this example that I have prepared is we want to use the parallel axis theorem to show that the moment of inertia of a rod rotating about an axis passing through its endpoint is 1/3 ml squared. Okay? So let's make a sketch first before we do anything else. So let me bring this back up. Okay, so what we want to do is we have a rod. We'll say that it has length L. And we know its moment of inertia about the center of mass because we have that in the table here, right? We have 1/12 ml squared. And you might be thinking, well, like we also have the, the endpoint one in the table, but let's pretend we don't. Let's pretend we had to calculate this, right, from first principles. So the center of mass axis is going to pass right through the geometric center of the rod, right? So we could say center of mass axis. And the primed axis is going to be at the rod's endpoint, right? And obviously you could have chosen the right endpoint, it doesn't matter, it's all symmetric. And we note that this is D, right? Because we're taking the axis from the center of mass and we're shifting it to the left, right? By a distance D. And of course D is just L over 2, right? And so let's write out the parallel axis theorem in generality, and remember that it said I prime equals I cm plus m d squared. And so let's fill this in. We have, for the moment of inertia of a rod about its center of mass, right, 1/12 ml squared. This is just from the table, and you're free, of course, to refer to a table like this whenever you might need to. And then over here we just fill in what D is, right? D, we said, was L over 2. Okay. So we have 1/12 ml squared plus 1/4 ml squared. And we can essentially do this. We can just write 1/12 plus 1/4, factoring out the ml squared. And this, of course, is 1/12 plus 3/12 ml squared. And we finally, upon adding the fractions together and simplifying, we would get 4/12, and that is, of course, 1/3 ml squared. And that is what the table tells us and what the problem statement says we should find, so that's good, right? So this is a very common example of how to apply the parallel axis theorem. We'll look at another example here, because I think the best way to just kind of make this clear is to work some examples. And this is going to be a bit more complicated. So I'll read the problem statement for you really quickly. You glue a solid sphere with mass big M, radius big R, and uniform density to the end of a rod with mass little m, length L, and uniform density. Taking the axis of rotation to pass through the very end of the rod, the end opposite where the sphere has been attached, what is the moment of inertia of this object? So let's make a sketch of this. And maybe you can already kind of see, but this is going to look it's going to look like a lollipop in essence, right? We're going to have the rod, and then we've glued a sphere to it, right? And so this is length L, and the radius is R for the sphere. Okay, so what we can do here is, well, first of all, remember that our axis, and this would be say like coming out of the screen or going into the screen, so I'll just draw an X, is going to be here at the end of the rod, right? So we already know that the moment of inertia of the rod about its endpoint is just 1/3 ml squared, right? Because that was what we just found here. So what we need to do is just use the parallel axis theorem to figure out what the moment of inertia of the sphere is. And I said it was a solid sphere, right? So I will write that down. The moment of inertia of the sphere about its center of mass is 2/5 big M big R squared, right? And that just comes straight from the table. Now what we need to do is we don't actually need to touch the moment of inertia of the rod because it already is given for the axis that passes through the rod's endpoint. But we do need to adjust the moment of inertia of the sphere using the parallel axis theorem, right? And so let's remember what that is. I'm going to write it more specifically this time. I'm going to say the moment of inertia of the sphere for our present case is going to be given by the moment of inertia of the sphere about its center of mass plus the mass of the sphere times the perpendicular distance from the center of mass axis of the sphere to the new axis, right? And the center of mass axis would be like that. And again, that would point into or out of the screen. And so that is going to definitely be parallel to the axis we are concerned with here, the one that we've drawn on the end of the rod, right? So we just fill this in. We have 2/5 big M big R squared. And then we have big M. The only thing we really have to change is this distance. And what I would say is that in this case, the distance you can probably see is going to be L plus R squared. Well, the distance is not squared, but there is a square in there. And that is just because this distance here is R, right? So we see that if this is D, D equals L plus R. Okay? Now, you might be thinking, okay, well, we got the moment of inertia of the rod. That was not too bad. Moment of inertia of the sphere. Now we need to like think about what happens when we connect them, right? When we glue them together. And the funny thing is that we can just add the moments of inertia together, right? To get the moment of inertia of the combined object. And this is because, right, remember, the moment of inertia is just defined to be a sum. We said it was I equals 1 to n m sub I r sub I squared, right? And if we, let's see here, let me put this in the document because I want to leave the sketch up, but I also want to write some stuff down nicely and neatly for you. So let me just say this. I'm going to say because of the way the moment of inertia is defined, and let's do this, let's rewrite it. We say it's defined to be sum. Well, there's no reason we can't just call this term that we're summing, right, the mass times the distance squared. There's no reason we can't just call that the ith moment of inertia. And what I'm saying here is I'm saying that we could express this like this, right? Where I sub I is defined to be m sub I r sub I squared. And the reason that I'm belaboring this is because I want to convince you that we can just take, for our present example, we can just add the moment of inertia of the rod to the moment of inertia of the sphere that we found using the parallel axis theorem. And that is perfectly okay. So let me just put that result down here. The moment of inertia of the lollipop is, and I'll call it I total, I guess. And this is just going to be moment of inertia of the rod plus the moment of inertia of the sphere, right? The sort of transformed moment of inertia. And filling this in, we find 1/3 m L squared plus 2/5 m r squared. And this is our moment of inertia of this configuration here. Yeah. And if you, well, actually you can't because I didn't give you any numbers, so you're just stuck with the symbolic result here. But if you really want to, you could make up some numbers, I guess. But that is how you would do this. And this is a general property of moments of inertia. Whenever we have some combined system, right, and we know the moment of inertia of each of the objects in the system about the same axis, we can just add all the individual moments of inertia up to find the total moment of inertia, okay? It's a very important idea, and it just comes back to the idea of the moment of inertia being defined as a sum, right? Okay, cool. So I think we're now in a position to state the rotational analog of Newton's second law. And what this looks like is this. And I'm going to continue to write the z subscript as long as I can remember to, because again, this is, you know, if we have a force vector and a position vector that are situated in the xy plane, then the torque that corresponds to those two will be pointing in the plus or minus z direction, right? And I think the textbook does this too. I'm not sure, but anyway, we state Newton's second law in rotational form as the sum of the torques in the z direction equals the moment of inertia times the angular acceleration, right? And so this is perfectly analogous to the form of Newton's second law that we all know and love, right? Where the net torque takes the place of the net force, the moment of inertia takes the place of the mass, and the angular acceleration takes the place of linear acceleration. And that's really it, right? Now, I just want to remind you that what this usually ends up looking like is we might have, like, let's say a couple torques in here, right? We might have like torque 1 plus torque 2 plus, you know, dot, 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 right? As many as there are. And this is because there can be, you know, multiple forces acting on an object exerting different torques. And we have to just take the vector sum to determine the net torque, right? That's what the net torque is defined to be. Very much like we did with Newton's second law. Okay, so hopefully this is not too shocking or uncomfortable for anybody. I want to wrap up here by just looking at some examples, and we will do more examples involving torque when we talk about static equilibrium, because the idea behind static equilibrium, and I'll state this in the next video, but the idea is just that we have some configuration where there's no linear acceleration or angular acceleration, right? And we just have certain things that we might be interested in solving for. And so we've already laid out the ground, you know, the groundwork for that. That's largely what we've been doing so far. And so for the next video, I don't really plan on talking very much about conceptual things. I probably will just try to do a lot of examples for you. And in those examples, you get more practice with torque. Okay, so let's look at this example though. A box of mass m equals 75 kilograms is hanging from the end of a uniform beam of length, I wrote length twice, 8.4 meters, and mass 45 kilograms, as shown in the figure below, when suddenly the wire breaks. If the moment of inertia of the configuration is 5.5 times 10 to the third kilogram meters squared, what is the initial angular acceleration of the beam as it begins to swing downward? So this is the picture, right? And here again, I'm going to use the whiteboard because when it comes to solving problems involving torque, even more so than Newton's second law, I would say drawing a very, very careful diagram is super important, okay? So that's what we're going to do. We're going to draw the beam. And notice that we can no longer do this thing that we were doing with Newton's second law where we just draw the object as a point mass, right? Because now we are very much concerned with the distance forces are from our axis of rotation, right? So let's draw the forces in. And this is, we're going to imagine now that the wire has already broke, right? And so there will only be two forces in that case. There's going to be the gravitational force, because the beam has mass, right? And one of the points of our discussion of center of mass was that when we have an extended object, we can imagine all the mass being concentrated at the object's geometric center, right? And for a uniform beam, it's pretty clear to see, I think, that the center of mass will be at the center, right? And that's part of the motivation for discussing center of mass, because now it's going to pop up a lot when we're talking about torque and static equilibrium, okay? And I'll fill this in even more, and maybe it'll become a little bit clearer if it's not clear already. So we also have this box hanging from the very end, and because the box has a gravitational force associated on, or acting on it, we're going to have a gravitational force basically, I mean, what this would actually be would be tension, right? But we could very quickly see that the tension force, well, the magnitude of the tension force equals the magnitude of the gravitational force on the box. So what I will write is I will just erase all this. and just call this big mg. Okay, and now we have to do a few things, right? We have to first specify our axis of rotation, and you might be like, well, it's pretty clear in this case, you know, it's probably just going to rotate about the hinge, and that is a very valid point. That is exactly what will happen here, but sometimes it's not so clear, right? So I want you to keep this idea of defining the axis of rotation fixed in your mind. But in this case, it is probably exactly what you would expect, and it's going to be there. So what we have is we have this distance is L over 2, right? And this distance is just the total length of the beam. So now it's just a matter of summing our torques. And let's see what that looks like. So also note that I am defining my x-axis to point like this, my y-axis to point like this, and my z-axis then will actually come out of the screen like this. And that's usually how we draw this. It's supposed to be like you're looking at an arrowhead that's pointing right at you, okay? And so here it's perfectly natural to talk about the torque in the z direction. So what we'll do is we'll write our expression, net torque in the z direction, and now we have to fill this in. So there's a sign convention associated with torque in as much as there's a sign convention associated with angular velocity and angular acceleration, right? And the sign convention is this. Any torque that tends to make an object rotate clockwise will be negative, and any torque that tends to make an object rotate counterclockwise will be positive, okay? And I was trying to be very careful when I stated that, because it is, I think, as I said in the last video, the exact opposite of what you would expect, right? I think it's natural to expect that clockwise is positive and counterclockwise should be negative, but that's not the case, right? So we have, remember our sign convention is counterclockwise is positive and clockwise is negative, okay? So with that being said, right, if we want to be very, very precise when we fill this in, what we would write is probably something like this. We would write negative mg L over 2, right? Because our R perpendicular for the weight of the beam is just L over 2. And then we could say minus mg L. And we could say that R perpendicular for the weight on the box is just L. And notice, right, if we were to draw a vector from the axis of rotation to either of these gravitational forces, there would be a 90-degree angle between them. And we did have one expression for the magnitude of torque that depended on sine, but sine of 90 is just 1. So that's why we're not writing this here. And the last thing to do is just say, well, okay, this equals the negative moment of inertia times alpha sub z. And I wrote a negative sign there because this is going to make me solve for the magnitude of the angular acceleration, right? Because I think we all know the direction, so we're just going to wind up with a positive number when we solve for this. So let's go through and get rid of all the negative signs. So rewriting this, we would have 1/2 mgl plus big M GL equals I alpha sub z. And to find the angular acceleration, all we do is just divide both sides by I, right? So we find something like this. And if you wanted to be fancy, you could factor out the GL, of course, right? And so if we did that, what we would get is little m over 2 plus big M divided by I times GL. And that's your angular acceleration. I am not going to get the number, but the unit should be radians per second squared, right? And so for those of you who like to go through and solve for the numbers, make sure as you do that you include your units and you see that it works out to be units of radians per second squared, right? Because that's what we expect for an angular acceleration. Okay, and I guess what I'll do actually before I move on is just clear this and make sure that we're all good on the note. Well, actually, no, I use the exact same notation in the problem statement to solve it. So I think that should be fine. Everybody should be clear on what represents what here. So I won't actually take any time to do that. Okay. Let's move on. We'll look at this last example here. And then we'll call it a day. Okay, so you push tangentially along the edge of a merry-go-round with mass 200 kilograms and radius 1.5 meters. If internal friction applies an effective torque of tau sub f equals 50 Newton meters on the merry-go-round, what magnitude of force must you exert to give the merry-go-round a constant angular acceleration of alpha equals 2 radians per second squared? So again, here we draw a diagram. So this would be like, I don't know why there's a bump there. Let's try this again. It's like really hard to draw circles on the tablet. So just bear with me. Okay, that's not awful. And so this is the top view of the merry-go-round, right? And we could say that our axis of rotation is at the center, maybe. And this will set us up to, it won't really matter so much in this case, but this will set us up to also use our x, y, and z directions from the previous problem, like so. Okay, so let's figure out what happens here. We have the radius is r, and we have that you are applying a force that looks like this. Remember, it says tangentially, and that means that the line of action of the force, right, it just intersects the circle once at one point. Okay, now you might be wondering like how I knew to draw the diagram this way, because this kind of indicates that the merry-go-round is going to, let's see, it's going to rotate counterclockwise, right? And we're not told in the problem statement what sort of directionality we have here, so I would say just choose whichever choice you like best. And in this case, I can do it this way, so I have that the torque associated with the force that you push is positive, right? And the frictional torque is negative, and I'll talk more about that in a second. So let's see, we've drawn our force in, we've defined our axis of rotation, so I think now what we do is we just solve this. So once again, I'm going to write the net torque in the z direction. And this is going to equal, now notice that if I drew a vector from the axis of rotation to the point of application of the force, again we would have that the force and the position vector are perpendicular to each other, so the sine of 90 is just 1, right? So we can simply write RF. Now, there is a frictional torque, right? And we don't know what the associated force is and what the associated R value is. But it doesn't matter because we're told in the problem statement that it has a magnitude of 50 Newton meters, right? So we can simply just write tau sub f. And remember that this is going to equal the moment of inertia times the angular acceleration in the z direction. And we're going to assume that the directionality of the angular acceleration corresponds to the direction of the torque applied by u, right? Which I think is a very sensible thing. I didn't state that explicitly in the problem statement, but I think it kind of makes sense because we don't expect that a frictional torque is going to be able to make something start spinning faster, right? Or even start spinning at all. So I think that's a sensible choice, and we don't need to really elaborate upon that. Okay, so let's see here. We are pretty much set to solve this, but what we have to do is we also have to substitute in for the moment of inertia of the merry-go-round, right? And I'll do that in a second here. But let me just rewrite this. And so what do we do about the moment of inertia of the merry-go-round? Well, I will always try to make it clear how to approximate something for any problem that I give you or that I write, except for this one apparently, but I'm going to talk about it so it's okay. And we could probably just approximate this as a disk, right? Because there might be, you know, some like bars that you can grab onto for support on top of the merry-go-round or something, but most of its mass is going to be due to the disc-shaped part. And so I think to excellent approximation, we can just say, well, the moment of inertia should just be 1/2 big M big R squared. And then the angular acceleration is what we want to solve for here, right? And again, it comes down to... No, it doesn't. I was going to say it comes down to just dividing both sides by the moment of inertia, but we actually want to solve for the force that you must apply. So let's do that. We're going to rewrite this as Rf equals 1/2 big M big R squared alpha, and then we just add the frictional torque to both sides, like that. And then all we have to do is divide both sides by R, right? And there you go. That's the force that you have to apply. I also will not calculate the number here, but I want to remind you that this should work out to be newtons for those of you who do end up calculating it, right? But this is pretty much it. And there isn't really even much we could do to simplify this, right? There's no mass to cancel. If we wanted to split the fraction up, we could like cancel a factor of R in one of the terms, but I don't think there's much of a point in that. So yeah, we're pretty much done. I just want to, before we conclude today though, I want to talk about some of the alternative definitions for calculating torques, and I'm not going to do this numerically, I'm just going to kind of show you what it looks like. And this will kind of be similar to some of the things we said about calculating work, right? So let's just draw sort of an arbitrary R vector and an arbitrary force vector. And let's say that our origin, or now our axis of rotation, because we are hopefully comfortable with that idea, is like this. So how could we represent the torque here sort of diagrammatically or pictorially, right? And what I would suggest is that we want to think about, and this is in one of the definitions I stated, right? Maybe breaking the force into its parallel and perpendicular components. And so that might look like this, right? And then I could call this F perpendicular and F parallel. And notice that the parallel component of the force contributes nothing to the torque, right? It might have some other role to play in a given situation, but as far as the torque is concerned, it's just wasted. It doesn't do anything. And so this is what we said, right, when we said something like, well, we can write that tau sub z is just r f perpendicular, right? And you could go about figuring out what f perpendicular is by just say, like, let's say we knew this angle here. We could say then, for instance, that, what was it? It would be cosine of theta. Now that's adjacent over hypotenuse, and in this case it's just f perpendicular over f. And you might be like, well, hang on, Ryan. You said that it's rf sine theta, right? Why would we do cosine? And that's a great question. But remember that in that definition where we said it's rf sine theta, theta was the angle between the force vector and the position vector, right? And those in general won't be the same. And so I want you to try to be flexible with the way you write torque, right? Not always expecting it to depend on the sign of an angle, because we see here, when we think about like the perpendicular component of the force, we get a correct expression for the torque that depends on cosine, right? And I think I want to do one more quick discussion of this pretty much exact same situation. So let me draw this one more time. I'm gonna clear my screen, so if you want to copy this down, pause the video really quickly and do so. But I'm gonna clear it now. And we're gonna do this one more way. I'm gonna try to draw it the same as before. I think it looks something like this, right? Now, another way we can think of this is we can do what we did in the very first example and just draw these so that they have the same origin, right? And that might look like this. And now let's say that we know the angle between them. Right, let's call this theta. This would be an example where sine is appropriate, right? Because we could also draw in the components of the force again. We could say, let me just draw in the parallel and perpendicular components. Now, this is parallel, meaning that it's parallel to the r vector, and this is perpendicular, meaning it's perpendicular to the r vector, right? And so now, in this example, if we were to write sine theta, this is going to be opposite over hypotenuse, right? So now it's f perpendicular over f, which implies that f perpendicular is just f sine theta. And in this case, the torque is r f perpendicular, which is rf sine theta. Now remember that this theta, right, symbolically is the same obviously as the theta we were using before, but it's not actually the same angle, right? It's just a dummy variable. It's just standing in for an angle. And so hopefully you're not too uncomfortable with the fact that I just previously wrote the torque as rf cosine theta, and now I'm writing it as rf sine theta because the thetas were different, right? And so if nothing else, hopefully I've given you something to think about and shown you that, you know, there are a few different ways of calculating a given torque, right? Okay, that's it. I will see you in the next video.